Hello everyone. So this is our second session. We have been discussing about derivatives and we got a few more topics to discuss today. And prior to that, let's see. I mostly used property or a rule of derivative, which we'll be using rigorously in our course. Suppose we have a function f of x, which is a quadratic function of the form a x squared plus bx plus c, where a, b, c are constants. Then f dash of x will be of the form 2ax plus b, where a and b are as same as in the definition of the function. Similarly, if f of x equal to just a linear function bx plus c, we have seen this in our previous class, then the derivative f dash of x will be just b, since the derivative of constant is 0. Yeah, that's what we are going to explain. Let f of x be the function f of x equal to, say, c, a constant. Then f dash of x will be nothing but just a 0. So the derivative of a constant function is always 0. The derivative of a linear function will be the coefficient of x, and this is how we differentiate a quadratic function. So we will be using these three rigorously throughout in our course, or the combination of these three. We can easily generalize this to higher order polynomials, which we may do in case of necessity. Right. So now we can go to the next concept of limits. In fact, limits actually, this had to be discussed prior to derivatives, but as I was oblivious to your textbook, I was compelled to start with derivatives and go to limits there. So what does the concept of limit express? Suppose we have a function f of x, right, or y equal to f of x. That's how we express functions. Y equal to f of x. Right. So as we make changes in x, the value of y or the value of f of x changes. For that reason, we call the variable x as independent variable and y as dependent variable, since y depends on x and x does not depend on anything here. Right. So as we make changes in independent variables, the dependent variable changes. Then the next question arises. Suppose we have a point x0. See, let x0 be in the domain or need not be in the domain. So let x0 be a point. We let our x, the independent variable or the argument of the function x, to move towards x0. So x is moving towards x0, and we examine where does y moves towards. Okay, so as x approaches x0, where does y approaches? That is the question, and from this point we define limits. Suppose y approaches a number L. Right, so what is the situation here? X moves towards x0, then y moves towards L. Right. If it is the case, we may say that limit x tends to x0, f of x equal to L. So what does this expression mean? Limit x tends to x0, f of x equal to L means as x tends to x0, this is how we express in the language of mathematics. As x tends to x0, f of x or y tends to L. As x tends to x0, f of x tends to L. That's what we express with the statement limit x tends to x0, f of x equal to L. Right. See, this is not actually, this is not the actual formal definition of limit, but we just need this. We can use this definition to work out problems on limits, basic problems on limits. Before moving any further, is it necessary that always there exists such an L. Suppose we let x2 move towards x0. Is it necessary that the value of y or f of x tend to a particular real number? Need not be. Need not be. There can be no number such that y turns to that number. Right. In that case, we say that the limit x tends to f of x0, f of x does not exist. Does not exist. So what I am trying to say is the limit of any function or it is not necessary that the limit of all functions exist at every point. Right. We may have a function f such that limit x tends to x0, f of x does not exist. We will see examples for this soon. We will see examples and things will be much clearer when we go through examples. Right. So for now, just keep in mind that it is not necessary that every function has a limit at every point. There may be limits or there may not be limits. Limits may or may not exist. Right. We need a few basic properties of limits to evaluate in the practical sense. We can call this as rules of limit or properties of limit, and for now, let me call them the basic properties. Basic properties of limits. Right. So, we make a few assumptions here. The assumptions are limit x tends to x0, f of x, and limit x tends to x0, g of x exist. Right. So, f of x and g of x are two functions. Limit x tends to x0, f of x, and limit x tends to x0, g of x exist. If so, here comes the first property or the first rule. Limit x tends to x0, f of x plus g of x equal to limit x tends to x0, f of x plus limit x tends to x0, g of x. Right. This is called the sum rule for limits. The sum rule for limits. This just says that the limit of a sum of two functions is the sum of limits of individual functions. Right. We had to find the limit of sum of two functions f of x and g of x here. So what we will do? We will individually find the limit of both functions f of x and g of x as x tends to x0, and we will just sum them up. This is called the sum rule for limits. Similarly, there is a difference rule which can be easily obtained from this. Limit x tends to x0, f of x minus g of x is equal to limit x tends to x0, f of x minus limit x tends to x0, g of x. Right. So, as in the case of addition, the same holds for subtraction as well. So, the limit of difference of two functions can be evaluated as the difference of individual limits of the two functions. Right. So, this is the sum rule, and we can just use the sum rule to deduce difference rule. Let's go to the next. The next is product rule. Limit x tends to x0, f of x into g of x equal to, as we expect, limit x tends to x0, f of x into limit x tends to x0, g of x. So as we have seen before, the limit of product of two functions is the product of individual limits of the functions. Right. Similarly, we have the division rule. We'll visit soon. Prior to that, let's see the reciprocal rule. The reciprocal rule, limit x tends to x0, 1 by f of x equal to 1 by limit x tends to x0, f of x. But remember, when we have a denominator, we have an obligation that the denominator must be non-zero. We don't know how to divide with a 0, so we assure that, or we assume that limit x tends to x naught f of x is non-zero. So if limit x tends to x naught f of x is non-zero, then the limit of reciprocal of f is the reciprocal of limit of f. Right, so this is the reciprocal rule, and we can use reciprocal rule and product rule together to deduce a similar or a similar division rule or a quotient rule for the case of limits. Right, then we have the constant function rule, which is limit x tends to x naught c. F of x is c here, just a constant, is nothing but the c itself, since c does not depend on x. Right, c is totally independent, so wherever x go, it does not matter for c, c will be c always. So limit x tends to x naught, c is nothing but c itself. Then the identity function rule. The identity function rule, limit x tends to x naught x. What is identity function? The function f of x equal to x is called the identity function. So we just replace f of x with x here. This is x naught. See, as x tends to x naught, where does x tends? See, x tends to x naught, then x has to be going to x naught itself. It's a redundant statement actually. So this is about the identity function, limit x tends to x naught, x is nothing but x naught. Right. So the next basic rule is, did I get the number wrong? No, I got. Replacement rule. Suppose this has to be written. I'll just clear this. Remember, limit f of x and limit g of x exist at x naught, or limit x tends to x naught f of x and limit x tends to x naught g of x exist. So the next rule is replacement rule. This is kind of a little more theoretical. Let fg has same values for all x near x naught. We have a point x naught, and we assume that f and g has the same value at all x near that particular point x naught. Not necessarily at x naught. Not necessarily at x naught. The value at x naught may change. We don't care. Right. If it is the case, limit x tends to x naught, f of x equal to limit x tends to x naught g of x. You may use this property in the future. So what does this say? F and g are two different functions, but they hold a property that they have same values at all points around or near the point x naught. F and g have the same point, the same value at every x near x naught. But it need not have the same value at x naught. The value at x naught at the particular point x naught may differ, but it has the same value around everywhere near x naught. If it is so, then limit x tends to x naught f of x is equal to limit x tends to x naught g of x. F of x can be replaced with g of x. Right. This actually depicts the beauty of the concept of limits. Right. Let's move on. So the next is, let's see an example. Before moving any more further. Let's evaluate the limit x tends to 3, 2x square minus 7x plus 3 by x minus 3. Okay, so this is a rational function. What is a rational function? Rational function is a function which is expressed as the quotient of two polynomial functions. this is a polynomial function and this is again another polynomial function. So this is expressed as a quotient of two polynomial functions, so it's a rational function. We will see a few ideas regarding rational functions on the go sooner. For now, let's examine this limit. So what does this expression mean? We are supposed to find the limit x tends to 3, 2x square minus 7x plus 3 by x minus 3. So this question actually asks us to find where does 2x square minus 7x plus 3 by x minus 3 go as we move x towards 3. So what does 2x square minus 7x plus 3 by x minus 3 goes as x moves towards 3. Let's examine. The first idea is to directly substitute 3 in the expression. Right, directly substitute 3 in this expression. But is that possible? When we substitute 3 in this expression, see, we have x minus 3 here. If we substitute 3 for x, we will have 3 minus 3 in the denominator, which is 0. Right, we don't know how to divide by 0, or we are not allowed to have a 0 in the denominator. So that is not possible. So what can we do now? Can we try to simplify this expression a little? So this is equal to limit x tends to 3. See, this is a quadratic expression which can be factorized as 2x minus 1 into x minus 3. You know how to factorize a quadratic equation or a quadratic form. Then we have x minus 3 here. See, now we can cancel out this x minus 3 and x minus 3. So what is left here? Limit x tends to 3, 2x minus 1. And now you can happily replace x with 3, which will give you 6 minus 1, which is 5. Right. So the answer is 5, or limit x tends to 3, 2x square minus 7x plus 3 by x minus 3 is 5. Right. So this is how we basically examine the limit. We will just try to substitute. If it doesn't work, we will try to simplify and substitute. We have a little more techniques to evaluate limit in a much more complicated cases. We will examine it soon. So now let's see a few more properties of limits, which are actually derived from those basic properties which we have seen a little ago. So the derived properties of limits. The first property is the extended sum property, or the extended sum rule, which says limit x tends to x naught, f1 of x plus f2 of x plus etc. plus fn of x is equal to limit x tends to x naught, f1 of x plus etc. plus limit x tends to x naught, fn of x. What does this expression mean? It's a long one, but a simple one. See, we have n functions here, f1 of x, f2 of x, fn of x. We assume that limit x tends to x naught, f1 of x exists. Similarly, the limit at x naught for f2 exists, and every function has a limit at x naught. That's our fundamental assumption. And we have to evaluate the limit for this whole sum. In the basic properties, we have seen how to evaluate the limit if we have a sum of two functions. We just extend that to the case of n functions by repeatedly using that rule, the basic rule, and we end up at the case where the limit for the sum of n functions can be easily evaluated as the sum of limit of n functions. Right. So this is the extended sum rule. Similarly, you can develop the extended difference rule by replacing this addition with subtraction. Right. The next rule is extended product rule. Extended product rule says limit x tends to x naught, f1 of x into etc. into fn of x is equal to limit x tends to x naught f1 of x into etc. into limit x tends to x naught fn of x. As in the case of extended sum, we have the product of n functions here whose limit at x naught is to be evaluated. So instead of multiplying all those functions and find the product, we can just find individual limits and multiply them all together, which will be much more easier than the other one. Right. So this is the extended function rule. And the third rule is constant multiple rule. Suppose we have a function f which has a limit at x naught. What we mean by that statement, limit x tends to x naught, f of x exists, that's all. So if it is the case, then limit x tends to x naught, c into f of x, where c is a constant, is c into limit x tends to x naught f of x. So the constant can be taken out of limit. Right, you can guess the reason. C does not depend on x. So C is totally independent of x. So there is no point in keeping the C inside. C can be taken outside. Right. Now the quotient rule. Limit x tends to x naught f of x by g of x. Suppose limit x tends to x naught f of x and limit x tends to x naught g of x exist. Then this will be equal to limit x tends to x naught f of x divided by limit x tends to x naught g of x, provided limit x tends to x naught g of x is non-zero. Remember, whenever you try to write a mathematical expression, if you have something in the denominator, make sure and assume that that denominator never takes the value 0. Right, since we don't know how to divide with the 0. Perfect. The next one is power rule. Limit x tends to x naught, x raised to n is limit x tends to x naught. Oh, sorry, it's this the power rule. So limit x tends to x naught, x raised to n is nothing but simply x naught raised to n. Right. Here we have a problem to raise. See, we assume that n is in the set of all integers. Z is the set of all integers, or to be a little more expressive, n can be 0, plus or minus 1, plus or minus 2, or any number. Right. N can be 0, or any natural number, or any negative natural number. Right. But what is x raised to minus 1? This is 1 by x, right? So, if this n takes a negative value, this will be nothing but 1 by x naught. In that case, if x naught is 0, we don't have any meaning for that expression 1 by x naught. So, we make sure that x naught is non-zero if n is negative. Right. We make an assumption that x naught is non-zero if n is negative. For the reason, if n is negative, x naught raised to n will be nothing but 1 by x naught, and if x naught is 0, then 1 by x naught doesn't make any sense. Right. So that's about the derived properties of limits. And before moving any further, I just want to re-emphasize a point that we have seen, or we have just said, that the limit for a function is not something obliged to exist, or it is not necessary that every function has a limit. Let's see a function whose limit does not exist at a point. Consider the function f of x equal to mod x by x. So you know what is the mod x? What is mod x? The absolute value function which makes everything positive or 0, whatever. So consider this function mod x by x. So how will the values of this function will be? What if x equal to minus 1? If x equal to minus 1, then f of minus 1 equal to mod minus 1 by 1, which is 1. Right. So what is f of 0? Is 0. Mod 0 by 0. Oh no, the function is not defined at 0. The function is not at all defined at 0 since we'll be having a denominator at 0. Right, so what is f of 1? Mod 1 by 1, which is 1. And we made a mistake here. F of minus 1 is mod minus 1 by minus 1, which is minus 1. And f of 1 is 1 by 1. Similarly, what is f of minus 2? F of minus 2 is mod minus 2 by minus 2, which is 2 by minus 2, which will be minus 1. And f of 2 is mod 2 by 2, which is 1. So if you try to generalize this, we will get to know that the value of this function for every negative number is negative 1, and for every positive number the function takes the value 1. And if we try to draw the graph, if this is 1 on the y-axis and this is minus 1 on the y-axis, the function will have, see, the function is not defined at 0, so we'll have a hole here. The function will be like this. The function will have this side for the positive numbers from the domain, and negative 1 for every negative arguments or the independent variable taking negative values. So don't get confused. I just want to express this function to show you that if we move towards x, from the left side, this is 0. So if we move towards 0 from the left side, from this direction, the function has the constant value minus 1. Right. So from this side we can at least conclude from this side that the limit will have the value minus 1. Right. But as we move from this direction towards the same 0, from this direction we can observe that the function takes the value, the constant value 1. Right. So that's a contradiction. When we approach 0 from two different directions, we get two different values. So in such a case, we fail to conclude to a single value as the limit of this function, and in such a case, we will say that the limit does not exist. Right. For such a function, the limit does not exist, and these functions actually give birth to another concept including directions, the limit from a single direction, which are just called the left hand limit and the right hand limit. I think we don't have that in our syllabus. I don't know whether we just need to check it out. So remember, it is not necessary that every function to have a limit at every root. This function does not have a limit at 0. Right.